All right, good morning, everyone. We have Dr. Manathunga from Middle Tennessee State University giving us his presentation on an epidemic compartment model for economic policy directions for managing future endemic. So I'll turn it over to Dr. Manathunga now to give us his presentation. Thank you so much.
Thank you for inviting me to your seminar series. And I'm going to discuss about epidemic compartment models and how we can use that in modeling economic policies. This research is a collaborative one. Dr. Senkala and Dr. Bichaka Fayasa, they are other collaborators in this research. So let me first go to the introduction. So infectious disease, they may have shocking effects to economies. So usually when we try to model economy, we don't think about the disease, we just model economy. And then usual approach would be you kind of like give a shock to the model. Like you give a shock to a parameter and then see what happens. For example, you can think if the disease comes, then maybe the labor force is going to deplete by this much. So you give a shock to that model parameter, and then you see what would be the outcome. However, it is more intuitive if you model economic policies based on the economic epidemic models. So in here, we try to combine epidemic models and the economic models together and get one output. So that's kind of like the whole like the summary of this research. That's what we are trying to achieve. So in this research, we are going to do several things. One is we have economic side. So we need to model physical capital, health capital. And then also other side, we have to model the epidemic. I don't know how many of you heard this name, SIR model. We kind of like extend that model a little bit. We call it as SIRV because we want to include the vaccination into the model. So once we have those two models, we combine both and to get one output. So in the SIRV model, we have susceptible, infected, recovered, and vaccinated. So we include the vaccinated into there. And the labor force consists of people who are not infected. So the labor force is going to be part of economic model. Now we are saying labor force consists of people who are not infected. Then that in that moment, we have a connection between epidemic models and the economic models. And also we consider parameters in SIRV model. For example, transmission rate, how fast the disease is going to transmit from one person to another person, and then how fast recovery. Now those things, we usually it's constant. That's how the people model it. But in our situation, in this scenario, we model it as a function of another variables, like how much money we really allocate to combat the disease, how much knowledge in the society, how much health capital is in that society. So based on that, then the SIR model also kind of like intertwine with the economic model. So we want to make everything together. So at the end, we solve the disease and economic models at the same time. So usually you may not have heard this one, learning dynamics. So we want to include the learning occur in the society. Usually when there is an epidemic, at the very beginning, there may be no knowledge about how to control. This is not the vaccine or the medicine, just the knowledge, like keeping 6 feet apart, that kind of knowledge. So we want to include the knowledge into the model. Usually it's intuitive in many ways. In any society, when there's a disease, people start to learn how to how to manage the disease. So that knowledge really help us to control the cost associated with the disease. So we won't include that one into our model. Any questions? If you want, you can stop me and ask questions. Also, we won't include health expenditure, but we want to make it differentiate between the general health expenditure, like what you spend for the hospital, just the general health expenditure, and the money we really allocate for the epidemic. So, for example, in the COVID, the government spent a lot of money just to find the vaccine specifically for COVID. So we want to distinguish that two components in the health expenditure. The general health expenditure that give the good health, and then when the epidemic comes, the direct investment to control the epidemic. So we have two types of health expenditure in our model. So the direct allocation to combat the disease, such as to do research and find vaccine and other cures. So before we continue, I want to give a little bit of what currently done on this topic. There are several research articles about this kind of research. Main one I'm going to discuss. I don't think I can summarize each and every research article in there, but this research article, it's really powerful one. I mean, it's kind of like the groundwork for this kind of research. The research done in 2014 by Goenka and Liu. So if we go to the reference, I can show the name. So they use very simple model. They use SIS model, susceptible, infected, and again susceptible. So you can go from one compartment to the other compartment. These are called as compartment models. So here you can see that they include birth and death. And also they include the transmission alpha and the recovery gamma. So this is a very simple model. Usually in epidemic models, we don't see the birth and death include, but they opt to include that in their model. Now what they did, they model alpha and gamma as a function of health. And where the health come from the economy, where the economy spend money on health. So that was kind of like a novel approach. So in this paper, they endogenized the parameter alpha and gamma in two sector growth model. So basically alpha and gamma depend on growth model. The growth model means basically the economic model. The reason is these parameters are not constant. They are going to change depending on how much money or how much effort we are putting into the controlling the disease. So they want to really see what is the effect. So once they have this model, they came up with the equations. So here you can see the equation. So what they do, they try to maximize utility. Utility is the happiness or satisfaction you get from consumption. Usually, there are different forms for this UC. You can see this equation UC. There are different forms. For example, log C. You don't get the utility like the straight line because, for example, let's say you consume 1 apple. You are happy. You like that. Then someone give 2 apples. Yes, you like, but if someone give 100 apples, then your happiness eating those apples is going to decrease. So it's kind of like a log function or some variant of that kind of function. So that's the utility function. Then you discount it to the present time. That's why this e to the power negative theta t. Then you don't want to just maximize that. There are some constraints. So you want to maximize it under consumption and the M. In here, M is actually health expenditure. So then we have this set of equation. Here we have the K is the physical capital, the dynamics or the differential equations or the law of motion for capital. You have the FKL, That is how the capital is produced. And then once capital is produced, we use it for either consumption. So we subtract C, or we use it for medical expenditure, we subtract M, or also that capital is going to depreciate like naturally. So delta K some depreciation, and it's also going to depreciate based on the difference between the birth and death rate. So we have that. Then also we have the generating health. We have health generating function, GM. Then it's depreciate based on some rate, and then based on the population. And then next we have the L dot, that is the equation for labor. You can see that the labor, differential equation for labor depend on the epidemic model. The labor is again used in the first row. You can see that it's used in the production function. So the labor force depend on the epidemic model, and it's used in the production function for the capital. So they are kind of like a join now. Then we have some conditions for the what are the to be non-negative consumption expenditures. So I don't want to go into the detail of the analysis since this is someone else's research. But I want to give some key results, what they found. There are so many results in that paper. Two of most important results, the way I think. One is the economy has unique disease-free steady state. So that means there's a state where the economy has don't have to worry, there's no disease. So at that point, don't spend money on the health expenditure. That is the implication. So don't just waste money on health because that's the optimal situation. Now, if the birth rate is smaller than alpha and gamma, which we use in here, you can see the alpha and gamma in here, or in this model, alpha and gamma. Then in addition to the disease-free steady state, there exists endemic steady state. Endemic means basically the disease is not going to die down. It's going to stay at some level. For example, like the flu. We can't really eradicate the flu. It's going to be in the society, but we kind of like learn to live in balance. So we have this endemic steady state where the disease is prevalent. At that point, you have two possibilities. One is either spend money on the health expenditure, like spend money for health, or don't spend money. That decision is based on the discount parameter, what we use in that model. So what the society used to discount, based on that, we have to decide whether we should spend money or not. That is the result of that paper. And then there are many other results too. Any questions? Okay, so let's go to our approach. So the first thing we want to do to introduce a new epidemic model. Now, if I go back to the previous one, this one is simple. It's S and I. Okay, susceptible, infected. So there's no recovery really. Once you infected, you come back to susceptible, or you have died. That is the only possibilities. So we extended that model, SIR model. So we have susceptible, infected, recovered. So we have these compartment models. In each compartment, there's possibility of death. The mu is death rate. We let it to be constant because if you change it, the model become really complicated. So we want to keep it at the same value, which make our calculations easy. And also we have separate compartment where we have the vaccinated people. So at very beginning, we assume P proportion of people are vaccinated. So then they are fully immunized. So they are immunized against the disease. Then the rest, they go through this compartment model in the SIR model. From S to I, you have the transmission rate beta, and then I to R, we have gamma. That is the recovery. I is infected, R is recovered. Once you recovered, we assume you are not going to be again susceptible. So the disease, you are immune to the disease. In here, you can see the birth rate. The population is not constant. It's depend on the population size, and there's a birth happening BN. Okay, so that's the new birth for the population, okay, which is common. Okay. So once we have this, we can before we now, so we have this model. Before I write the differential equation, I want to discuss about that learning. So remember that I mentioned there's going to be learning occur in the society about how to control the epidemic. So the differential equation for that, there are several approaches. One approach is this one. You assume it's just depend on the it's a product of these two components. A is direct investment, E is the existing knowledge, and delta is some constant. Okay. That is one approach. Or we can, E is the knowledge. E is the knowledge. Okay. So E is the disease controlling knowledge. Or you can assume it's going to be look like this. In here, we have the e to the power phi and a to the power lambda. The phi is spillover of knowledge. That means basically when you have more knowledge, it's kind of like a spill to the other area. So you can create more and more knowledge. Lambda is stepping on toes. That means basically you spend money on the same thing. Like you give grants to two different research group, but to do the same thing. So it's kind of like a waste if they both come the same thing. So stepping on toes. So it's kind of like a reduce the effectiveness, but the fee kind of like a make it grow more. So these are the some possibilities for knowledge production function or the dynamics of knowledge production. For us, we came up with this one. So we assume, okay, you can come up with a function for here. It's up to you. Okay. But then the knowledge is going to decrease at some rate. For example, we don't know how to build pyramids now. That knowledge is gone. So the knowledge really decreases over the time. So that is why we assume the knowledge is going to decrease at some point. Even if we ask from society, do you remember how you control Spanish flu during 1970? That knowledge may be not there. It's forgotten now. So the knowledge kind of like a decrease at some rate. So this is the now, this 4.1 is the equation for knowledge production or the dynamics of knowledge production. Okay, so once we have this, we can write the, before I go to the equations, let me come back here. So here we have this beta, and gamma. Usually in SIR mode, these are constant. You just get some values. Okay. Beta is transmission rate, gamma is recovery rate, which is 1 over time you spend on the infectious compartment. But but we assume that they depend on these three. A, which is direct investment to control epidemic, E, existing knowledge, H, and the health of individual. So we assume that transmission rate really depend on those three. And the recovery also depend on, again, A, E, and H. So they are not constant, they are not functions. And also we assume birth rate and the death rate, they are constant. So they are constant. And the death is negligible compared to the population. This is true. Even with the COVID, the death is negligible compared to the total world population. Okay, this is true. And we also assume that the fraction of population vaccine time t is in between 0 and 1. So we have this model. So the total population at time t is the sum of people in S compartment, I compartment, R compartment, and V compartment. That's the total population. So we have now the disease dynamic for epidemic model. We have the differential equations. So I can write right away the dynamics. The people are coming at 1 minus TB rate to the susceptible compartment. Then they become infected at this rate. And then, then some leave by the compartment because of the death. The same thing happened with the infected. They come from susceptible compartment, then they leave the infected compartment either by recovery or by the death. Then whatever left from whatever come from the infected, they come to the recovered and they leave that compartment by death. In the vaccinated one, the only way they can leave is by death. Then once you add all of these SIRV, we get the dynamics of the total population, which is B minus mu and T. B is birth rate, mu is death rate. So then we can kind of like define the fractions. Okay, so we really don't worry about the total size. It can change. So we went to the fractions. What is the fraction or you can say proportion of susceptible, proportion of infected, proportion of recovered? Then we have to find the differential equation for that. So we take this one and we differentiate using quotient rule, and we come up with this kind of equation. We can do the same thing for the others, and once we do that, we get these other formulas. So we have the dynamics for the fraction of susceptible, infected, recovered, and vaccinated. So once we have this, the first thing we want to do, find the steady states. The steady state means basically you set this derivative to 0 and you solve for S and I. So in here you can see the disease-free. When you have the disease-free equilibrium, that means basically when there is no disease, we have the solution S to be 1 minus P, I to be 0 because there's no disease. So there cannot be any infected in there. And the rest of the population, not in the susceptible, they need to be in the vaccinated, and the recovered is 0. We want to find the equilibrium of this steady state. So we take the Jacobian and we calculate the eigenvalue. And we know that if all eigenvalues are negative, then the solution is stable. So once we calculate that, we can see that it's going to be stable if this is true. You can see that all of these are negative, so there's no question about that. But this eigenvalue is going to be negative if this is true. So we come back to that. What we do, we define the reproduction number. So we define it to be R naught. R naught is going to be beta over B plus gamma. Usually in the reproduction number, if R naught is less than 1, then that means it's going to be disease-free. If R naught is more than 1, that's going to be endemic. That means the disease is not going to be died out. So we want to define that quantity. So then we can see that. So now we have these values, and for the disease-free, and we come back to the endemic state. When we solve for the endemic state, then we have the S star to be gamma plus B or beta, I to be this, and the other quantities in here. So you can see that we have two steady states. One is a disease-free steady state. The other one is endemic steady state. So again, we want to discuss about the stability. Remember that when you solve a differential equation, you really want to know whether that solution is stable or not. So we check the again eigenvalues, and one of these eigenvalues are not really simple. So we define X And then using that X, we can write the eigenvalues in this form. You can see that this one and these two are really negative. So in order to make it stable, we need this one to be negative. So we can easily prove that. If 1 minus p time r naught is more than 1, then endemic state is stable. What we do, we take the determinant. So we have the determinant of this matrix, and determinant is positive. If determinant is positive, that implies that the product of all these four is positive. So that means this one cannot be negative because three of these are negative. So this one should be negative in order to have the product to be positive. So from that, we have the eigenvalues are negative and endemic state is stable. So then we can create the bifurcation point. Basically, you graph the infected versus the R naught. So you can see that when you come to this point where the R naught is 1, if it is more than 1, then we have the stable endemic state, steady state, which we prove right here. And if it is less than 1, we have stable resistive steady state. If it is more than 1, then we also have resistive steady state, but it's going to be unstable. So this is the forward bifurcation diagram. Okay, so that's the analysis of epidemic model. Next, we go to the economic side. So in the economic side, first we need the utility function. So we don't want to keep track of individual health histories. That is hard. So we have to make assumption that every individual is identical. So we use the large representative consumer idea. So we assume that economy is populated by identical consumers whose consumption is same. Otherwise, it's going to be like for one person, you have write one utility function, which is not easy. So we have the representative model then. Once we have this, then we have the social planner problem. The social planner try to maximize this function. He or she want to maximize the utility for the society, but under some consumption, under some constraint. So in here you can see the C is consumption, theta is the discount factor. We need to discount the total consumption. The consumption to right now, and then get the total consumption, present value of total consumption. So social planner faced following problem: how to choose consumption, general medical expenditure, and direct epidemic control to investment AT. So the person need to think, okay, how to divide the investment into these three components: for consumption, and for the medical expenditure, and for the direct investment control epidemic, such that the total consumption is also maximized under given constraint. So what are the constraints? One constraint is the labor is going to be some of these susceptible, vaccinated, and the recovered. These are the only ones available for labor. So 1 minus IT. So labor is going to be 1 minus IT. So also we want to assume that there are 3 production functions: 1 for physical good, 1 for health, and 1 for creative knowledge. The creative knowledge one we already discussed. The physical goods are either consumed, invested again, spent in health, or depreciated. So that's what is going to happen to physical good. So the production function of that physical good depend on capital and labor, where labor depend on the healthy individual in the society, number of healthy individuals in the society. So we have this function. We have the law of motion for the capital. So we produce, we make capital, and then we separate, we give it for consumption, or we give it for medical expenditure, or we give it for direct investment to control epidemic, or it depreciate based on the depreciate rate and the birth and death rate. Then the health, again, we develop it, and then it depreciate. Okay, so it depreciate. At this point, we have like, let's say 9, not 9, maybe 11 assumptions. These are the first few assumptions I want to share. So there are a series of assumptions we need in order to make this work. For example, we want birth to be more than mu. Then this transmission rate function, we need to satisfy certain qualities like partial derivative respect to each one is negative, which is true because once you increase the direct universal control epidemic, the transmission rate should decrease. Once you increase the knowledge, it should decrease. So that's true. And the second order need to be positive, and beta approach to some constant value when we approach to 0. So these are some assumptions. I'm going to skip it. If you need it, we can come back. But there are 9 assumptions in our model. I mean, at very beginning. Then we add a little bit more assumption. So in here, let me go to this assumption. This one is a little bit useful to know. This one called the Inada condition. Sometimes you may hear this. Under Inada condition, we assume that this one is continuous and positive component of the Hessian is negative definite. And when k goes to infinity and k goes to 0, how the first derivative respect to k behave. So we have some assumption on that. Same with the g. And the utility function, you can see that it's first derivative is positive, second derivative is negative, so it's decreasing. I mean, it's concave, and then when c goes to 0, you have u prime infinity. At times, I mean, when the consumption is like right, when you just start consume, you get more happiness or more pleasure. Okay, so let me skip this assumption. So here is our model. You can see that we try to maximize based on x and y. X is our control. So we are controlling consumption, medical expenditure, and direct universal control epidemic. And our state variables are the capital, health, susceptible fraction, infected fraction, and the knowledge. And under these differential equations, okay, we have some constraint. Any questions? This is called as a social planner problem. Okay. When you see other research papers, you see the social planner problem, but it may be different constraint, but usually it's same in here with those control and state variables. So once you have this first thing, we want to do 3 things. One is first you want to show there is a solution for this setup. Otherwise, there's no point. So there is just the optimal solution. Once you prove there is a solution, what is it? How do you find it? So we want to find the necessary and sufficient conditions. Okay, so those are the things we want to do. So in order to show there exists optimal solution, we use a theorem proved by another researcher. Okay. But let me discuss why we cannot use traditional approach. Usually, when you want to show that there exists optimal solution for optimal control problems, you can use Mangasarian sufficient condition or arrow sufficient condition. Let me go to what that means. Mangasarian sufficient condition says, okay, take that current value Hamiltonian. You can write a Hamiltonian based on those differential equations. Then prove that it's concave with respect to all state and control variable. However, for our one, this is not easy because it's known that SIS, SIR dynamics are not convex. So we cannot apply Mangasarian sufficient condition. Then for the arrow sufficient condition, we want to take the maximized Hamiltonian respect to control variable. Then we want to show that it's concave with respect to state variable. So again, this may not be true in our situation. So what we do, we use a similar approach given in that Goenka paper, one I mentioned in 2014 paper. Even though their model is simple, they had like approach. And so we are going to use the same approach. So we use the axis optimal solution. Then we calculate the steady state using first order necessary condition. Then we prove that it's optimal using sufficient condition, proving sufficient condition. So for existence of optimal solution, we use theorem 1 given in another research paper in 1998. So in there, let me show the theorem. So this is the theorem written by them. So they claim that if you have this kind of setup, then there exists optimal solution. They don't give the what's the solution. They just claim there exists optimal solution if it satisfies this assumption. Okay. So since these assumptions, you can see that that's why we made some assumption at very beginning. There are 9 assumptions for us because we want to make our model also like a way we can use with this theorem. Okay. So this theorem is very powerful one because it's very general setup here. So anyone who want to apply it, all they need to do, they need to come and they need to prove that their system is satisfying this assumption. Once they can prove that, they can go back and they can apply the theorem, where the theorem says that under this assumption, there is a solution. So what we did, we proved that. Let me share my screen, another screen. So here you can see that I didn't include these theorem lemmas, but what we do here, we have like a series of lemmas where we prove that our setup satisfies those assumptions. That's all we are trying to do. We are trying to prove that our setup is satisfying those assumptions. So basically, we have maybe 3 or 4 lemmas which try to claim that our setup satisfy those assumptions. So we want to claim that our model satisfies these assumptions. Assume the following. Then we can use their theorem. This is their theorem. Then you have the solution, the axis solution. So we have so we apply that and then we claim the axis social plan of the solution. So that part is done. Then come the steady state. So we want to investigate the steady state of social planner problem at optimal. We already did that for the epidemic model, but not for the economic model. So we want to now include everything and study the steady state solution. So what we do, let me go to the Lagrangian. So we write the Lagrangian. So this is the current value Lagrangian. Current value Lagrangian, and then we take the first order conditions. Okay. So these are the first order necessary conditions. You take the derivatives, and these are the first order conditions. I mean, the first 3 need to be equal to 0 if the solution is maximum, and then maximum need to satisfy this condition, and then the other ones you have these other conditions. This is true. I mean, any optimization problem, you do this calculation. Okay. And then we have we have this constraint and these equations, and then we have this transversal condition. What happened at the end? What happened at the infinity? So we define it to be this. And that's what we need. So first thing, so we want to calculate what are the steady state. So steady state, I mean, basically you solve this equation. Okay, so you calculate. So before that, we need another assumption. We want second derivative of knowledge production function is not equal to the, I mean, the first derivative of knowledge production function respect to knowledge is not equal to the discount factor and the rate of depreciation of knowledge. Okay. Otherwise, it's going to give us a constant to be 0. So we want that to be 0, not 0. So the first assumption, the first proposition after that would be there exists decision steady state with this solution determined by this. So here you can see that before I go to the proof, here you can see that if there are no diseases in the society, don't spend money on the general health, and the health is going to be 0, and the susceptible population is going to be 1 minus p, infected population is going to be 0, and the knowledge is going to be 0 since there's no disease, and the investment we spend on the controlling that is 0, and the K star and the consumption are given by these. So that's the decision steady state solution. So we can prove it. I want to skip it since we don't have that much time. Next one would be, okay, what happens if you have endemic steady state? So the endemic steady state exists if and only if it satisfies this constraint, if there is a solution to this system. So we come up with that, and then we really go more detail, and then we find a solution. Okay, so first step would be endemic steady state exists if there is a solution m star, k star, a star, e star, h star to following set of equation and inequalities. So we can prove mathematically if there's a solution, then there's endemic steady state. If there's endemic steady state, then it satisfies this solution. Here you can see that the first one, what we saw at very beginning, endemic steady state exists only if R naught is more than 1. So that's that one. So here, maybe 2 more constraints. You can see that I include L without defining what is L. This is not labor. This is another constraint. The reason I use L, the literature is using that notation. So it's kind of confusing with labor and L, but I just want to go with the literature without coming up with new notation. So they use L for labor and L for this kind of like quantity. So we keep that notation. Before we further characterize this endemic steady state, we need a few results. First one is assumption. We assume that L quantity, which we have here, decreasing with respect to A, E, and H. Excuse me. Then we can prove that at 0, L theta J, this one is dependent on theta and J both. One second. So here you can see that we have theta and J both. So it's dependent on theta and J and AEA. So what happens if at 0, respect to theta, we can prove that this one is decreased. So here we have assumption, but here we can really prove it once we have this assumption. So now we want to analyze endemic state. Remember that we said, okay, there exists solution, but how do you find the solution? So we want to divide theta into kind of like a range. So first we come up with theta 1 hat, theta 2 hat to be solution to these equations. We have these equations, theta 1 hat, theta 2 hat. So then we try to analyze what happens if theta is less than theta 1 hat b, theta 1 hat b in between, and if it is more than both. So what would be the scenario? So that we want to analyze that, the solution for endemic state. So first one is if theta b is less than b is in here in this range, and if they are then we have the unique solution to this theta 1 hat and theta 2 hat, because first that we need that, because we want to show that there's solution, because otherwise someone claim, okay, how do you know that there is those theta 1 hat, theta 2 hat? So we want to prove that there's solution. Then once we have that, we define two quantities, theta max to be maximum of these two, and theta minimum to be maximum of these two. Okay. Then using that that quantity, we can characterize the endemic state. Again, we want a little bit more detail. So we analyze those functions, G, which is production function for health, F, which is production function for physical capital, K is capital, L is labor. So how those change with AEH. So we prove that the derivative of health production function decrease with respect to AEH when they are increasing, and so forth. We have 5 results. Once we have this, we can come up and we can characterize the endemic state. So the first one is for each fixed B, if theta is more than, remember the theta is discount factor, if theta is more than that constant, then there is unique steady state solution for system given in that setup. In other words, when theta is more than theta max, there is unique endemic steady state without health expenditure. So without health expenditure and without direct investment control. So that's really a surprise, because it says, okay, disease is there. However, if theta is more than that quantity, don't spend money on for health. There's no point. If the discount factor is more than that quantity, then even though disease is there, don't spend money. It's not the optimal. Next one is if theta in between, assuming theta max is theta 2, then we have another answer. Then there is a unique endemic steady state with 0 health expenditure and non-zero epidemic control. So in this case, say, okay, don't spend money on general health, like for hospital, not hospital, like let's say, like just to increase the health of society. Okay. But spend money on controlling the epidemic. Okay. So based on where the theta is. The last one is if theta max is theta 1b, then don't spend money on controlling epidemic, but spend money on the general health expenditure. So we have a theorem with the proof. So I skipped the proofs, then they are more technical in detail. So once we have this, we want to discuss the sufficient condition. Remember, all of these are necessary conditions. So how do we know that those are really sufficient? So we want to claim these solutions indeed optimal solutions, proving that sufficient. So we can write the Hamiltonian. Earlier I wrote the Lagrangian, now I wrote the Hamiltonian, okay, with the first order necessary transfer necessary conditions. Okay, so we have this. Once we have this Hamiltonian and the first order conditions and transfer necessary conditions, I go back to the Mangasarian sufficient condition. Remember that Mangasarian sufficient condition says what? It says Lagrangian function must be concave with respect to both state and control variable over open convex set containing all the admission value of the state and control variable. So proving that is not easy. The one way to prove that it is using Hessian and prove that it is negative semi-definite. In order to do that, you can take the principal minor and then show that they are alternate sign, so that order ones are non-positive and even order ones are non-negative. However, we came up with this one of principal minor, which is hard to know whether it is positive or negative. Okay, so we cannot really apply Mangasarian theorem. And the arrow sufficient condition, again, it's hard to apply. You take the maximized, which I mentioned earlier. So what we do, we take this Hamiltonian, and we go straight to the theory. I mean, we prove it straight using a path in the using a path. Let me show what we are doing. So here, let me skip these two slides. So what we do, we take any path and we prove that it is local optimal for social planet problem. So under those, if we have a local path which satisfies those necessary condition, then it is really local optimal. So that's what we are proving in here. So basically, that would prove that those solutions coming from first order necessary conditions are really optimal. Okay, so you take any path which satisfy these necessary conditions, and then you prove that that solution is going to be optimal. So this is what we want to prove, which we can do. So once we have once we've done that, let me go to the solution because I have maybe like 7 minutes. Okay, so optimal solution is given endemic steady state. If we have this path, then it is going to be optimal, locally optimal for the social planet problem. So that is, this is need only to be done for endemic steady state. The disease-free steady state, that's always optimal because it reduced to the neoclassical growth model. So in that setup, we don't need to think about it. This only about this one, endemic steady state, where the disease is there. So let me give the conclusion of the research. This research developed a framework to incorporate epidemic model into economic models. Epidemic model model using economic parameters like health, direct investment to control epidemic and learning. The economy has unique disease-free steady state. At this stage, don't spend money on health or controlling epidemic. However, if you are in endemic steady state, we have three possibilities. One is, so in order to define that, there exists two constant. And if the discount rate theta is bigger than both of these constant, then there's a unique endemic steady state without health expenditure and without direct investment. So don't spend money on health at all. If it in between, then we have two possibilities. One is zero health expenditure, but positive investment to control epidemic, or positive health expenditure, but zero investment to control the epidemic. So that's kind of like a summary of the results we got from this analysis. For future work, let me give some future work. So I would like to analyze how to price things like annuities. Let me share my screen. So for example, let's say we have two compartments like susceptible and infected. So let's say we have insurance, where the insurance, when you are in this stage, you pay premium. And then in this stage, when you are infected, you collect benefit. We can really expand that idea. Okay, so how do you really price that kind of insurance product? The other one is bonds, pandemic bonds. And the pandemic bonds first issued in 2017 by World Bank. So basically you issue bond and the money will come to you. It's not you, actually it's a country, come to country if the country is in epidemic situation. So how do you really price that kind of bonds based on the epidemic model? So that is two possible research question for me, for you, for future work. This idea, same idea, like how do you include the epidemic model in the economy? Annuity pricing, insurance product pricing, or like bond pricing. So that's future work. Okay, thank you. Any questions?
I have a question, Dr. Manathunga. How did you decide on the assumptions that you had?
Assumptions really come with once you are proving things. When you are proving some results, it comes to some point like you really cannot go further without you making assumption. So that's when you go back and write the assumption and then come back to proof. But it's not like we first wrote the assumption and we say, okay, that's what our assumption. It's like when we are proving in general setup, we come to some points where we need assumption. So
How do you assess that those assumptions are reasonable? Like they might be easy for the math, but then if they reflect reality, are they reasonable?
yeah, so right now we are doing the numerical calculations. Some of these assumptions may not really real in the real world, but we try to go with the other research done in the similar fashion. So we hope that it would hold when we do the numerical calculations. Yeah.
Thank you. Any other questions? All right. If not, let's give our speaker a big hand.
Yeah, thank you again for asking me to come and present it.
Yeah, thank you so much for coming and speaking to our student chapter.
Okay. See you later. Bye.
Awesome, everyone.